Great. Okay, well, welcome everyone for the first lecture of Digital Design and Computer Architecture. We're doing it online again. Last year we started in person, but then we switched to online. This year we're also doing live streaming on YouTube, so you can actually do it you can actually watch it over there. And if you're not at ETH, also you're very much welcome to watch this lecture or also future lectures as well. Okay, so this is going to be Digital Design and Computer Architecture. It's a bachelor's course, second semester. If you're at ETH, you probably know that very well. It's a required course. And let me first start introducing myself. I'm a professor at ETH. It's been about 5 to 6 years since I've been here. Before that, I was a professor at Carnegie Mellon University. I still have one PhD student left at Carnegie Mellon. And after that, I will not be at Carnegie Mellon officially, let's say. I got my PhD from UT Austin, worked at a bunch of companies during my PhD and after my PhD. As you can see, they're listed over here. So hopefully I will bring about some of the industrial experience and industrial connections I have to the perspectives you will receive in this semester. And if in future semesters, if you decide to take some other courses from us. Let's see. Okay, if you can reach me with this email address. I also have an ETH email address, but this tends to be more reliable in general. And you can find information on my website, including links to these classes, as you will see later on. I do research and teaching in computer architecture, computer systems, hardware security, and bioinformatics. We're going to talk a lot about computer architecture clearly here, but we're going to also touch upon different aspects of computer architecture. We do a lot of work on memory and storage, hardware security, safety, predictability, fault tolerance, robust systems, hardware-software cooperation, which is going to be important in this particular lecture especially. And we look into a lot of architectures for bioinformatics, health, medicine, and intelligent decision-making. So I'm quite excited about all of these areas. So our current research mission is really building fundamentally better architectures, and that requires understanding all of the components of a modern computing architecture. And this course is really about the fundamentals of understanding these computing architectures. So hopefully you'll be interested in all of the aspects of computer architecture as much as I am. So these are some current directions we're following in my group: fundamentally secure, reliable, and safe architectures, fundamentally energy efficient architectures, more memory-centric architectures. You will get exposed to it during this lecture and in during the course as well. Reducing the latency of existing architectures, making them much more predictable and robust, and designing architectures for future applications like AI, ML, genomics, medicine, health, etc. Important applications. This is my research group. Actually, this is a picture that was taken before the pandemic. That's why everybody's together, as you can see. Well, not everybody, because there's a remote component as well. You will see that many of these folks in the picture are actually going to be your teaching assistants or student assistants. And this is the motto of the group, as you can see over here. And we actually have a newsletter. If you are interested in learning about the group, you can read this newsletter. Hopefully it's accessible to folks who are just starting their undergraduate degrees in computer science or electrical engineering. It should be interesting. And you can see that this is the current state of affairs with Zoom pictures. Okay, let me introduce myself a little bit based on where I'm coming from. Hopefully you can get a good idea of your lecturer. And that gives you an idea of my mindset. So I strongly believe in what's written on this slide. I believe teaching drives research and research drives teaching. So innovation is all built on these two components in the end. So teaching drives research, meaning that by understanding the fundamentals, you can actually do something fundamentally better and improve the state of the art, make lives better, as we will discuss. And research drives teaching, because once you actually figured out a better way of doing things, that becomes a fundamental component for future generations. So research, essentially, research 10 years ago becomes education 10 years later, let's say. So in a sense, teaching is all about educating someone about things that is already known by almost everyone, by essentially everyone, let's say, in the state of the art. Whereas research is very similar to teaching. It's really about educating folks about things that no one else other than you knows, perhaps. And I believe this is actually a very healthy loop. This is unfortunately my looping construct in PowerPoint. There's a better construct you can clearly come up with, but I like this one because it's clean. this is essentially a loop. Basically, teaching and research feed each other essentially forever. Okay, so this is another principle. We focus a lot on insight, and I encourage a lot of new ideas. So if you come up with any new ideas during the course of this course or later, feel free to contact me. If you don't get a response, please contact me again, because my email tends to be not so reliable, because I receive a lot of email and it's not easy to respond to everything that comes. Focus on learning and scholarship. This is important. Clearly, you're just starting your studies, especially if you're at ETH. So this is, I think, a pillar. And on top of that, this is what we do in my research group. I'd like to create an environment that values free exploration, openness, collaboration, hard work, and creativity. And I think these 5 pillars are important for both teaching and research. And I think in the end, I'm a strong believer in the quality of what you produce. That really defines your impact overall. And I think that's again true for teaching and research. Okay, so that's a little bit about philosophy. I have a lot of lectures online. If you're interested in learning more about some of these things that we've already discussed, you can go and watch these lectures. I don't think a lot of them require a lot of background knowledge, or background is given in those lectures. Some of these things we're going to cover during the course of this bachelor's course, but clearly we're not going to go extremely advanced during this course. And if you're interested in more views on computing research and education, you can actually watch this interview that I gave to some students after receiving an award this is not last year anymore, it's the previous year. And they asked a lot of good questions. So I like this interview a lot. And there's more. You can see a lot of material basically on my website in terms of what I think about topics. Okay, so how to approach this course? Let me also mention this, because this course is not an easy course. It's a heavy course. Clearly, ETH is a top place, and especially the first year classes are not easy. But these are some of the words that were used by previous takers of this course. They found it a formative experience. And I like this word phrase, because I think this is a really great way of approaching this course. In the end, your grades, yes, are going to be important, because unfortunately, you're going to be evaluated based on an exam in this course. But I think the best way of approaching this course is really taking it as a formative experience. And hopefully exam success will come along the way. Unfortunately, yes, you have to pass the exam so that you can continue your studies. But I think this course has a bigger role than just an exam in the end. Think of this as a formative learning experience. And this is another set of words that was used by one of your peers who took this course in the past. They said it's high investment, high return. And I think in banking terms, it's not a bad analysis. And I also like thinking of this as essentially a learning experience. So I would like to reduce the focus on the exams and the grades, but focus more on the learning experience. And hopefully you will get to learn long-term trade-off analysis. And hopefully that will enable, I think my big focus is going to be on critical thinking and decision-making. And hopefully this course will enable you to, with the skills toward that direction, because we will cover a lot of concepts in computer architecture and design. And I believe those concepts are actually much more generalizable than the limited field of computer architecture that we're dealing with today. Okay, as I mentioned, we're going to cover concepts and ideas. We're going to focus a lot on fundamentals, because this is the first course. We're also going to talk about cutting edge, because I believe that fundamentals and cutting edge also relate to each other. Today's cutting edge is going to be tomorrow's fundamentals. And I think hands-on learning is going to be important, because you're going to do the labs and do the hands-on learning during the labs. So this course actually brings you the conceptual view as well as the hands-on learning view. So hopefully it's going to be a good experience for people, and hopefully you're excited about it. Now, having said that, if you have taken this course in the past and if you have done the labs, I would not encourage you to do the labs again, because that's going to be additional work. If you've already done well in the labs, I would encourage you to use your grade. And my TAs are actually posted something on Moodle so that you can say, okay, I'm going to use my grade from the past as opposed to doing the labs. And again, if you've gotten a really good grade, I would suggest using your grade. Hopefully you learned basically in the end. Okay. So now with that background, let me jump into what we will learn in this course. I must also mention that my lectures tend to be relatively high bandwidth. This was mentioned to me many times in the past, but I think the best way of approaching them is really not trying to take notes, not trying to read everything on the slides, but trying to take this as more of an experience, like almost like you're watching a movie where you really try to understand what is coming out of my mouth as opposed to what's written on the slide necessarily. So slides are essentially cues for what is going to be described. I mean, you can take notes, of course, but don't get derailed by just taking notes. We're going to put all the slides online. All the videos are clearly online. Just take maybe simple notes that are not necessarily that you find really important. So in the end, everything is online. You don't need to be taking notes. If you're a note taker, if you learn by that way, of course, I'm not going to say you don't take notes, but beware that we'll go at high bandwidth. Okay, so let's start with what will we learn in this course. Essentially, the answer to this is hopefully we're going to learn how computers work from the ground up, from the very basics, essentially. And also, we're going to learn why we care. I'm going to focus on why we care today. I guess, why do we learn that? Well, I guess if you ask that, then there are multiple answers, because you're going to be computer scientists and engineers. And I think it's critical for people to learn how computers work as opposed to not know how computers work. I see a lot of unfortunate cases where people just do programming without knowing exactly how those programs get executed in a computer. And I think this is a bit sad, in my opinion, because in the end, it's not magic, right? In the end, there's nice infrastructure that enables us to execute this. And if you actually understand that infrastructure, you can achieve a whole lot more, even if you end up becoming a programmer that is relatively far away from hardware. And hopefully I will convince you in this particular lecture. So why do we have computers? I will rephrase this as, why do we do computing? And the answer to this is to solve problems in the end. So why do we solve problems? So that we can gain insight into the problems we're having, right? And I would recommend folks to look at Richard Hamming's, this beautiful book that talks about how computers are designed for insight. The goal is really not to generate numbers, but actually to generate insight that can help solve the problems. Okay. And of course, why do we need this? To enable a better life and future, hopefully, right? That's the goal in the end. Of course, technology is agnostic to betterness, let's say, or betterment. Technology can be used for good or bad, but hopefully we'll stay positive in this course, and we'll try to make technology for the good into the future. Okay, so then the next question is, of course, how does a computer solve problems? And that's what we're going to focus on in this course. And the high-level answer is by orchestrating electrons. At least in today's dominant technologies, computers orchestrate electrons and enable electrons to do the things that will lead to the solutions of the problems. Okay, so how do problems get solved by electrons? That leads us to the transformation hierarchy over here, which is basically we start with a problem, and we need electrons to solve this problem. Clearly, we cannot speak electron language. At least so far, we have not figured out how to speak that electron language very well as humans. So we have abstraction layers built into it. We translate the problem to an algorithm. Algorithm gets written in an implementation in a programming language, and then that gets executed on top of some system software. And that also gets translated into the software-hardware interface, which are the instructions. And then that gets implemented. The instructions get implemented in microarchitecture, as we will discuss a lot. And those get implemented in the logic gates, and then those get implemented by the transistors and different kind of devices, capacitors, for example, which operate based on the principles of physics and electrons in the end. So this is the transformation hierarchy, and this is where computer architecture sits in that transformation hierarchy. It's really the hardware-software interface and the implementation of it, microarchitecture. But this is a very narrow view, and I will hopefully convince you in this lecture that it's a narrow view. We're going to focus on this expanded view of computer architecture going forward. But of course, this course is limited. Even though we're going to focus on the expanded view, we're going to spend a lot of time in the software-hardware interface and the microarchitecture. So expanded view is really about algorithms to devices. I'm going to give you examples of this from today's designs. Okay, so levels of transformation. Let me go into a little bit more of this. I'm not going to go into a lot of detail. Your books, actually, the recommended books cover the levels of transformation, especially Pat and Patel book. As I mentioned, the purpose of computing is to gain insight, and this is Richard Hamming with his cat, as you can see over there. And we gain and generate insight by solving problems. The key question is, how do we ensure problems are solved by electrons? essentially that brings us to transformation hierarchy. So let me go into a little bit more into the transformation hierarchy. Problem gets translated to an algorithm. An algorithm is something that's essential for being executed on a computer. It's really a step-by-step definition of a procedure that has three properties. Essentially, it has a property of finiteness, which means that it's guaranteed to terminate. Each step is precisely stated. This is definiteness. And each step can be carried out by a computer, effective computability, right? So there are steps that cannot be carried out by a computer. For example, I don't know, you can imagine expressing steps that way. And those should not be part of the algorithm definition clearly. Okay. Again, there could be many algorithms that have these characteristics to solve the same problem. For example, if I'm a human is a computer, let's say, and I want to go from here to Stadelhofen station. To be able to do that, I have an algorithm, right? And the algorithm can try to minimize the distance from here to there. It can minimize the time from here to there. And it needs to be ending. It needs to be definite, step by step, computable by me. And it also needs to effectively computable each step. For example, if one of the steps involves going from here to Stadelhofen, I have to jump over a building, that's not going to work, right? Because I am not capable of executing that step as being a computer, right? So that's an example of effective computability. Okay, next is programming and language. There are many, many languages. We're not going to cover that in this lecture, but you're taking other courses. And then runtime system and then ISA. Let's focus on the ISA a little bit because we're going to spend a lot of time on it, especially early on. ISA is the instruction set architecture. This is really the interface or contract between software and hardware. This is what the programmer assumes hardware will satisfy. So this contract will specify a lot of things, including what the instructions will do. And we're going to focus on that a lot, as I said. Microarchitecture, we're going to focus on this a lot also. This is really one implementation of the ISA. So today, for example, we have the x86 ISA, ARM ISA, and MIPS ISA, and many other ISAs. RISC-V is another ISA, for example. It's an open ISA. Microarchitecture is an implementation of the ISA that satisfies the contract. There may be many, many implementations of the ISA, as we will see in this course. Some of the implementations underneath basically do things that the ISA doesn't talk about, but the implementations don't expose that to the program. So they still satisfy the contract, but they do very, very interesting things like out-of-order execution of instructions so that they can actually maximize the performance of systems. Okay, and that microarchitecture gets implemented in logic gates and logic structures. This is essentially what we will also talk about. We'll start with actually, these are digital logic circuits. These are building blocks of the microarchitecture like gates. And then they're built based on transistors like devices. So in this course, we're going to focus a lot on the logic microarchitecture ISA and touch upon programs, runtime systems a little bit, algorithms also. But main focus will be the box over here, as you see. But we will start with a transistor as an abstraction. We will abstract it as a light switch, for example, and then build logic gates on top of that and Boolean algebra on top of that. Okay, so hopefully this gives you an overview. So what is computer architecture given this? So the way I like to think about computer architecture is it's really the science and art of designing computing platforms. And that's it. That's a general definition, right? And this includes the hardware. This includes the interface, hardware-software interface. This includes the system software, in my opinion, and the programming model. So this is an expanded definition, as you can see. And it's not just science, in my opinion. It's also an art because these computers are going to be running workloads that we don't know of. They're going to be out there maybe 10, 20, 30, 40 years, who knows? So they could be executing things that we have no idea they would be executing when we're designing them. A design of a computer takes anywhere between 6 months to, let's say, 5, 6, 7, 8 years. And you take that time to design, but the computer will be operating in the field for 40 years, let's say. And it may operate, right? My cell phone is 6 years old, for example. So how do you make it a science? Well, it's very difficult. If you want to really, truly make it a science, you have to be able to model into the future 40 years, let's say, or even 5 years, or even 1 year. Who can model into the future for 1 year and figure out what workloads will be executed on this device? So you really need to make decisions based on art and experience as well, in addition to science. That's why this is really a combination of science and art. I think that's true for a lot of engineering fields, but more so in fields that are relatively fast moving, where you don't know what's going to happen into the future. And of course, the goal of designing this computing platform could be multiple. And these are called design goals. Basically, we design these systems to achieve a set of design goals. And design goals depend on what kind of system you're designing. For example, one design goal could be, I would like to achieve the highest performance on Earth on workloads X, Y, Z. So this could be the very high performance computing systems, right? Supercomputers, for example. And then another design goal could be, I would like to achieve the longest battery life at a form factor that fits in your pocket with cost less than some number of Swiss francs, or whatever your favorite currency is. Now, this sounds like a mobile system, but a very different design point than the supercomputer, right? Supercomputer doesn't have to fit in your pocket, for example. So it has very different thermal and energy and power and cooling requirements compared to your cell phone, let's say. Another example is, I would like to get the best average performance across all known workloads, or all workloads that I care about, at the best performance divided by cost ratio. And again, this is what's called general purpose computing in general. So this is where Intel and AMD, for example, design systems that are general purpose. And this is a very different cost and design point compared to the previous two. And you can keep expanding it. For example, you can say, I care about only one workload, but I don't want to have a supercomputer. I want to have a relatively specialized system. And we're going to talk about those actually in this particular lecture also. So there may be many, many, many different computing platforms that you design. For example, I want to have the best AI ML inference engine accelerator that operates with mobile computing constraints, right? And that's going to be important, increasingly important going into the future. And that's happening today. And that's another design point for a computing platform. And usually you have different metrics. We will talk about those metrics, especially in the next lecture. Maybe today we will not go into that. And usually you evaluate designs based on metrics. And there are many, many metrics you evaluate designs with. You can actually come up with 10s, 20s of metrics. But sometimes some of these metrics are more important. Some of these metrics are more important than some other metrics. So it's important to keep in mind that this is really about design and trade-offs. And the course will focus on the design and trade-offs. But in the end, designing a supercomputer may be completely different from designing a smartphone, but many, many fundamental principles, trade-offs, and decision-making are actually similar. And that's where hopefully this course will be very useful to you, and I will give you that perspective. In the end, the fundamental building blocks are quite similar, and the trade-offs you make may be different, but the trade-off space you're dealing with is going to be very similar. Okay, so I will leave it at that and give you some examples of different computing platforms. Let's just show you some examples. These are some things that you may have, you may be used to. Some of them are old, clearly. These are some other computing platforms, right? They're used for different purposes. Clearly, the design point is very different. This is another computing platform. This is clearly a self-driving car. Well, kind of. And it's a joke from Mr. Bean, of course. But it raises a lot of questions, actually. This is really a computing platform in the end. And do you really trust your self-driving car this much to be able to sit on it comfortably and do what Mr. Bean is doing over here? I would argue that we are not at that point in computing today. So our design points do not really fully enable this sort of self-driving today. And we're going to talk about that in this lecture and in some other lectures as well. Not necessarily directly, but the design decisions we make are going to affect things like self-driving cars and how much we can trust them, for example. Okay, this is another example that I just wanted to show this. This is one of one of the Google's self-driving cars. You can see the computing infrastructure in the back so that the self-driving car can do vision processing, machine learning, etc., so that it doesn't hit a pedestrian, for example, and it can stay on the road for it. This is another computing platform. This is a data center. It's more general purpose. It can execute many things, but clearly you can see that the form factor of this is very different from what we have seen earlier. This is another one that looks kind of similar to the data center, but it's actually very different. This is a supercomputer. This was one of the fastest supercomputers, Tianhe 2. I don't think it's the fastest anymore, but I like this picture, kind of. It looks similar to the previous one. This is really designed for high-performance scientific calculations, best performance in the world. Okay, this is another example. This is a machine learning accelerator that was designed by Google. It's called TPU, Tensor Processing Unit. This is the first version of it. And we're going to cover the fundamental principles that this particular machine learning accelerator is based on when we cover the systolic arrays lecture. It's essentially a systolic array-based processor. You will see that later on in this course. And the whole purpose of this is really to accelerate inference in machine learning. Basically, train a model, and then that model basically predicts or classifies some images, let's say. It doesn't have to be images, but it could be any input that you give to it. And that classification task is intensive in terms of multiply and accumulate operations, for example. And those classification tasks can be performed much faster using the specialized systolic array engine that essentially pumps data in and pumps outputs out over here and does multiplication inside this array while the data is flowing. And we will cover the fundamental principles of this, but I wanted to give you this as an example of today's computing platforms that are specialized for machine learning. This is really specialized for machine learning. And this is one example also of the algorithm architecture device co-design that I mentioned, cutting across these layers as opposed to just looking at the hardware-software interface and the microarchitecture. This is really, you design the algorithm such that it can execute nicely on this systolic array, for example. Okay, I'm going to go into more details when we talk about systolic arrays. I'm going to show this picture actually later in this lecture as well. So this is another example. Tesla, a car company, actually designed these chips so that they can do specialized vision processing and machine learning on their self-driving cars. And they decided to design their chips because it was important for them so that they could actually customize the chip to the workloads that are running on their system. So imagine this is a car company designing chips, right? That doesn't go well necessarily, but it does go well because they have to customize the computing requirements of the workloads that they're running are so intense that they have to customize the hardware to the algorithms that they're deploying in the field. And they actually add other features like better multiple chips operating together so that they can have better redundancy, better safety. And you can see some of the numbers over here. If I go back to Google, Google essentially made the same choice. They basically said, okay, we have these workloads that are intensively executing machine learning inference in our data centers. They're consuming a lot of energy and they're slow on existing systems. How do we actually accelerate them? And they decided the right answer, or the cost-effective answer and high performance and energy efficient answer for them, was to actually design their own chips that are customized for those workloads. So this is what I mean by algorithm architecture, device co-design, customization across the stack. And this is happening in many, many domains, as you can see. Traditionally, software companies are becoming hardware software co-design companies. Traditionally, car makers are becoming hardware software co-design companies plus car makers, as you can see. So I'm going to show you more examples of this. But this is my axiom going forward. Essentially, if you would like to achieve the highest energy efficiency and performance, as well as reliability, let's say security, some other metrics. But let's start with energy efficiency and performance. If you would like to do that, we really must take the expanded view of computer architecture and co-design across the stack hierarchy, algorithms to devices. And this enables us to specialize the system, overall system, as much as possible within the design goals so that we can achieve the design goals. So hopefully I'll give you some more examples of this. So with that in mind, let me talk a little bit more about why studying computer architecture is exciting. And I'm going to give you some examples in this lecture of what's happening today in computer architecture and cutting edge. So in a sense, if you're worried about the exam in this lecture, relax, because this lecture is really going to be motivation for all of you. I don't think any questions will really come up on the exam related to this particular lecture. But I think it's really important for you to understand for the rest of this course, as well as your careers and hopefully your life. I would like to think of it that way. But computer architecture this is another definition. It's really the science and art of designing, selecting, and interconnecting hardware components and designing the hardware-software interface to create a computing system that meets functional, performance, energy consumption, cost, and other specific goals. Okay, why do we want to do this? And hopefully I showed you earlier, but we would like to enable better systems. And if you want to enable better systems and better life, you want to make computers faster, cheaper, smaller, more reliable, more secure, more robust, etc., so that we can solve big problems, right? And I will actually point you to some other lecture as an optional assignment where you can get extra credit for when we talk about enabling better systems. So we would like to exploit advanced and changes in underlying technology and circuits. On top of that, we would like to enable new applications. For example, computer architecture actually has enabled new applications like machine learning. The reason why machine learning is extremely successful today is because GPUs were able to train algorithms that were developed decades ago. And when GPUs became successful parallel computers that are general purpose, GPUs are graphics processing units that everybody's using today on their cell phone or laptop, for example. When they became successful parallel computers, other folks who are doing machine learning said, okay, maybe we can use this to train our algorithms, train our models. Maybe we can use them to do inference. And they basically essentially did that. And because of that, the machine learning revolution is really taking place today. Artificial intelligence and machine learning revolution. So there are other examples of this, like self-driving cars clearly relies on vision, machine learning, etc. but it came about because of, again, the processing power provided by computer architecture. And lifelike 3D visualization 20 years ago, virtual reality, those are interesting things, again, that require very intense computations that are extremely energy efficient, potentially, depending on what you do with the virtual reality, right? If I have a headset, virtual reality headset, I don't want my head to burn while this headset is doing accurate computations, right? And then personalized genomics and personalized medicine, which we are hopefully going to talk about toward the end of this lecture, is another new application that I believe is actually extremely promising and extremely data intensive. So the list goes on, actually. The list was a little bit less updated. For example, video. Even video is an application, but today we take it for granted, right? But if you go back 40 years ago, the computer architectures at the time were not fast enough to do good video. But today we can do much, much better video, like the Zoom streaming. So our infrastructure in computer architecture has developed a lot to enable these applications. And some of the applications we're taking for granted. Maybe 40 years later, we're going to take self-driving cars for granted also. And that will be because of this computer architecture advances, as well as the hardware software co-design that I mentioned so far. Okay, on top of this, we would like to enable better solutions to problems. Software innovation is actually built on trends and changes in computer architecture, as I mentioned, the machine learning revolution, for example. And over time, more than 50% performance improvement per year has enabled innovation. This is a number from general purpose computing. But for special purpose computing, this number can be much, much higher, actually. Like orders of magnitude improvements are actually possible if you're specializing your system to a particular application. And finally, we would like to study computer architecture so that we can understand why computers work the way they do, right? So that we can fix them whenever they're not working, or we can make them better, right? And I think this is actually a very, very scientific part of it, because if it already exists and if you're trying to understand it, you can essentially apply all of the scientific principles completely without actually resorting to a lot to art over here. Okay, so today is actually a very exciting time to study computer architecture because industry is in a large paradigm shift to novel architectures. There are many different potential system designs possible. And when I say industries, it's actually the innovation industry in general. It's not just the chip industry, for example. It's not just the software industry. It's really the innovation industry. So a lot of, for example, Tesla has nothing to do with software or chips, right? But they're actually designing novel architectures so that they can improve their system designs, right? And this shift is really motivated by many difficult problems. And also, it's caused by the shift as well. So we have many difficult problems motivating the shift. We have many difficult problems caused by the shift at the same time. So we would like to solve all of those problems. And I'll give you, I've written some examples over here. I'm not going to talk about all of these. I'm going to give you some examples in these lectures that you will see. But clearly, we have a huge hunger for data and new data-intensive applications, hopefully for the good. We have significant constraints like power, energy, and thermals, depending on the design constraints. Designs are becoming very complex. Technology is becoming not so good in scaling, as we will discuss. We have big memory and data bottlenecks. We have reliability problems. We have programming issues. We have huge security and privacy issues actually in computation today, both general purpose and special purpose. And there are today no clear and definitive answers to these problems. As a result, people are actually exploring new paradigms and new novel architectures to solve these problems. And actually today, computing landscape is very different from what it was 10 to 20 years ago. I actually took my first computer architecture course, just like you're doing, in my bachelor's second semester, actually, at the University of Michigan, from a person who would become my PhD advisor later on, Yale Pat. And that was in 1998. That's 23 years ago, right? And when I was taking that course, the computing landscape was extremely different than what it's today. So today is much more exciting, let's say. I was always excited, clearly, about computer architecture, but today, computer architecture is everywhere. We are basically changing the systems. At the time I was studying, we were focused on essentially single core processors, simple single core processors that are optimized for doing one thread execution really, really well, high performance. Even energy efficiency was not that important at the time. We're talking about 1998, right? So over time, over the course of like 23 years, things have changed a lot. And I'm going to show you some examples. Today, both applications and technology demand novel architectures and designs are actually responding to them. Basically, today, every component and its interfaces, as well as entire system designs, are being re-examined. And I hope to show you some examples of this. And these are some components. I've given you some examples, like we have heterogeneous processors and accelerators. many processor accelerators. We have hybrid memories, hybrid storage, persistent memory and storage, GPUs, AI and ML accelerators. So some of the things actually don't exist in this picture clearly, but they exist in architecture. So today we're at a very interesting place. And I think the axiom I mentioned earlier, I'm not going to repeat it, but basically we really need to understand the importance of this axiom. We really need to take an expanded view, because that's what's going to enable the next generation of revolutions in systems. Let me give you a historical perspective also. This, I think, this is going to be a little bit philosophical, but I think it's important for freshman students to be exposed to these bigger concepts in life, let's say. So many people probably know about Richard Payneman. He is a famous American physicist. He won the Nobel Prize at some point in his life. But basically, he's known for many things, especially for his passion for teaching. I think that's very important. But he's also known for this phrase that's called, "There's plenty of room at the bottom." And what he meant when he said this in 1959 was that essentially devices and circuits, mostly devices actually, present a huge opportunity for us to improve and innovate the systems that we're designing. He actually mentioned, for example, direct manipulation of individual atoms using devices so that you can have synthetic chemistry that's much powerful. And then later, actually, this talk was relatively unnoticed, let's say. You can see the Wikipedia over here. Nanotechnology advocates, who are actually quite successful today because nanotechnology is everywhere today in design, they basically use this talk to establish the scientific credibility of their work. But other things that Feynman imagined in this talk was basically denser computer circuitry. Clearly, this is 1959, right? This is actually before Moore, Gordon Moore, mentioned his law. That was 1965, as we will discuss in the later lectures. He basically suggested it should be possible in principle to make nanoscale machines that arrange the atoms in the way we want and do chemical synthesis by mechanical manipulation. And he also presented this idea that I like, which is basically essentially a surgical robot, right? Swallowing the doctor, he said over here. So these are basically things he thought would be enabled by extreme innovations at the lower level of the stack, devices and circuits. Remember the transformation hierarchy? This is devices and circuits. And I actually believe that there's a lot of opportunity still at this lower level of the stack. We just need to find it. It's becoming harder to find that opportunity, but we need to find it. So devices and circuits still present huge opportunities, in my opinion, and I'm going to justify it in a little bit as well. So clearly, if people are exploring actually graphene-based circuits today, for example, there are other circuits that people are exploring. Quantum is one example. I believe those are all going to be part of the equation into the future. But there's also another perspective, which is there's plenty of room at the top. This was written more recently. This is actually a consensus view, almost, let's say, that most people are thinking that as technology scaling becomes difficult at the circuit and device level, we should explore more at the software, algorithms, and hardware architecture layers, basically. Basically, opportunities for growth in computing performance is going to be available and be even more important at the higher levels of the stack. So why am I telling you all this? I think I don't subscribe to either of these, basically. I think I would revisit my axiom saying that I actually believe that there's plenty of room both at the top and the bottom. We need to investigate it and need to find it, but we can actually do much more than we could do individually at the top and the bottom when you can actually communicate well between and optimize across the top and the bottom. So it's really about algorithms to devices at the bottom. You can optimize them both, but you can get much more by communicating between them more and optimizing across the stack. And I'm going to give you some more examples of this. So that's why we have this expanded view. And hopefully I've given you the historical perspective of this expanded view as well. Okay, so now let's jump into the things that I believe are exciting that are happening in computer architecture today. And I'll give you a sampling of what I believe is happening, including something that has happened just last week. So you're going to be really at the cutting edge by listening to what comes. But I'm not going to start with that. So I'm going to basically first talk about issues that are the interesting things that are happening related to performance and energy efficiency. And this is one example from 2019. So if you took this course before 2019, you wouldn't have seen it. And this is called non-volatile memory. It's based on Intel's 3D X-point, cross-point technology. You can see that this is very similar to your main memory DIMMs, right? Modules, but except it's not DRAM. It's not dynamic random access memory. If you, well, you probably know that DRAM, dynamic random access memory, when you power your computer off, it loses the data. As a result, you have to have a hard disk, for example, that's slow, or SSD that's slow to back up your critical data. This thing over here replaces DRAM potentially, but it doesn't lose its data on a power loss. So it sounds great, right? This is non-volatile memory, essentially, main memory. Its speeds are comparable to DRAM. Today, it's not as close, but it's much closer to DRAM compared to flash memory, for example. So it's actually competing with DRAM today. So this was not around until 2019. Now it can enable a lot of innovation, right? This clearly was enabled by a lot of innovation at the device level. So this is based on some technology called phase change memory. It's fundamentally different from dynamic random access memory. We're going to talk about that later on. This technology required a lot of work to make it work, essentially. And that took more than 10 years or so for many, many companies to work on it. Intel was the first one to release it to the public. As you can see, you can buy it actually online and put it in your systems, assuming that they're capable of using this, of course. So this can enable a lot of innovation in operating systems, applications. For example, I mean, one very simple example could be very fast hibernate, right? You don't need to actually, your DRAM, you don't lose data when you turn off your DRAM in this case, assuming this is your main memory. So I think this is very exciting. Just to give you an idea of how long it takes to get to these innovations, clearly there are no innovations at the device level. There are innovations at the architecture level also. So we actually did some work on this topic. We're actually doing some work on this topic still, but we did some very preliminary early work in the area. This was published in ISCA, the major computer architecture conference, in 2019. We were looking at this topic in 2007. And basically we were actually exploring the idea of, can we replace dynamic random access memory with phase change memory? And we were doing these studies 12 years before Intel actually released their chip. So we were actually imagining the future as architects and trying to replace it with a better future, let's say. But this also gives you an idea that you may have a great idea potentially, but that idea may not be realized for decades. In this case, we're actually lucky. It's only 12 years, let's say, from concept to realization, let's say. And this is another paper. If you're interested in reading it, this is a easier to read paper, let's say, that talks about phase change memory technology, at least our perspective of it's when we developed it at the time. Okay. So, okay, let's move from memory to something else. This is another example that's happening today. This is, again, announced in 2019. Let me look at something on the right side. Right side is the largest GPU comparison, right? GPU clearly has been around for a long time. GPUs are old right now. I cannot talk about GPUs anymore as something new. But these are some of the very capable computation engines, right? GPUs, 21.1 billion transistors, NVIDIA Titan GPU, right? Titan 5. And it's big, 815 square millimeters. Well, these folks at Cerebras designed a chip and a machine that's much bigger. The chip itself, you can see that it's 46,000 square millimeters. It's a wafer scale engine. So normally you start with wafers, you cut it into pieces, and those pieces become your chips. These folks said, no, we actually want a chip that's much more capable. We want to accelerate these machine learning training workloads so that we can form the model. And we want a lot of computation capability, multiply and accumulates, that are very close to huge amounts of memory. How do we get that? Well, let's make the wafer the chip. And that wafer now has a lot of computation elements, as well as a lot of memory next to it. I believe, don't quote me on it, but I think they have 18 gigabytes of SRAM. That's really very close to the computation units over here. So this, you can think of this as a near data processing engine. But basically, that was their purpose. And then they specialize the system so that they can execute machine learning workloads. They have an algorithm, compiler, programming language, etc. flow, so that they can compile these machine learning training and inference workloads such that they can execute it on their chips. So it's a full system design, which is very similar to what we've discussed earlier. So clearly there are a lot of challenges to this. It's a startup. It's not been successful yet, but they've actually released platforms that are potentially being used by some big players. We don't know who they are necessarily. It could be the governments, for example, that could be building models. Not necessarily for the good, by the way, but again, technology is agnostic. But essentially, this system needs to have very high power requirements, for example. How do you cool this huge wafer that you can hold in your hand, right? How do you actually power up that huge wafer? How do you ensure that it operates reliably? Whenever you have a fault in any part of this chip, how do you ensure that that fault doesn't affect the whole system? Because the probability of a fault in a given chip now increases because chip is the entire wafer, right? So there are a lot of issues that span the system stack, but this is happening today. It was not easy to imagine that this would happen 10 years ago. Well, I think if you're a computer architect and looking forward, yes, you could imagine it. But for the regular folk, let's say, it's not easy to imagine. So by the way, I should go back over here to phase change memory. This also has an algorithm architecture co-design. You need to design the system to take advantage of this non-volatility and persistence, actually. I did not go into it, but I'm happy to talk about it later on. Clearly, this is kind of outside the focus of this course, but if you're interested, you can read these articles, for example. But these are both algorithm architecture device co-designs. So another example, this was actually also developed in 2019. This is processing in DRAM engine. Normal computers, as we will see in this course, are actually bringing data from memory to the processor so that the processor can process it. These folks at UpMem basically enabled a paradigm called processing in DRAM in memory. And basically, they put processors inside the memory chip. Simple processors. And they're not extremely capable because you cannot fundamentally, the process technologies that you use to design memory chips, main memory chips, and processors are actually not as compatible. So these folks actually did that. Now you can actually do the processing next to the data without moving the data outside the DRAM chip. Now, this is great because moving the data outside the DRAM chip actually costs a lot of energy and a lot of performance. So you can gain a lot of performance and energy back by minimizing the data movement. So this is actually very fascinating, in my opinion. And this is happening today. We actually have access to these chips. We actually have experimented with them. We actually see a lot of benefits. And we actually are going to publish a paper soon related to this. And at some point, if you take the advanced course, you will actually learn a lot more about this. But this was not imaginable 10 years ago also. I mean, even myself, who has worked on processing in memory, for example, did not think that this would be coming as fast as it has come because of the resistance sometimes that you see to new ideas, as we will see. Okay, now let's go to something that has happened last week. This is also in the processing in memory space. And you can see that this is press release by Samsung, which is clearly the major memory company. There are three major memory companies. Samsung is the one that has the highest market share, let's say. And these folks basically said they have developed a new processing in memory architecture that is specialized for machine learning applications, let's say. And they basically claim that they can reduce the energy consumption by more than 70%, as you can see. So this is actually very exciting, in my opinion. And you're lucky that this course started 1 week after the ISSCC conference where this was announced. And you can see, again, I don't expect you to understand all of this clearly. We're going to start from the basics later on, like not in the next lecture, but next week. So hopefully we'll build up to these. But just to give you an idea of the complexity of the systems today, this is based on something called high bandwidth memory. And you can see that they're stacking. They're really stacking layers of chips. And you can see that there are some memory layers over here, and there's some compute layers, like FIMDRAM layers. So there's some compute capable memory layers that they have. And you can see that I'm not going to go into the terminology. You can read the paper or look at the presentation. But these compute processors inside the DRAM chip, DRAM layer, inside the memory layers over here, can do floating point multiplication, accumulation, addition, and multiply and accumulate, as you can see, which are heavily used by machine learning workloads. Clearly, you can use this for other workloads as well, right? That can benefit from this. But clearly, this is designed with machine learning in mind so that you can accelerate those workloads, because that's the workload that's really experiencing huge bottlenecks in terms of both energy and performance today. Okay, cool. Let me give you some more examples over here somehow. Okay, I don't know what's happening. Okay, so this is another example. Again, I'm not going to go into the details of this, but you can see that this is a diagram from the paper that they published a week ago. You can see that some of the principles that we're going to see in this lecture are actually employed in this processing in memory engine. So this is what I meant by fundamental principles that we're going to cover. So you're going to see how a pipeline operates, how their register files, how you can control them, how you can sequence through instructions. You can do that on the processing side. You can do that on the memory side over here. So you can see that the fundamentals you're going to learn in this course are going to be applicable to different places in the computation, different places in the platforms. And function memory, even though it's a new concept, it's taking advantage of some of the fundamental building blocks to enable computation next to memory. And we're going to talk about instruction sets, for example. This particular processor that they have next to memory has an instruction set. We're going to see a much bigger instruction set, but they have a subset of these instructions over here, as you can see. So hopefully, this gives you an idea. And this is the real chip implementation that they showed last week. You can see that there's digital register transfer level language, which you're going to be exposed to in this course a lot. You're going to do the labs in register transfer level language. We're going to talk all about that. We're going to talk about course logistics, and we're going to talk about what we're going to cover. We're going in the labs and lectures, but they're going to happen next week. This first week is all about motivation, so that you can understand the importance of what's coming, and also you can get acquainted with the cutting edge that's happening in the field, so that you can see what kind of revolutions might be happening across the stack. Okay, but they basically put a lot of work into designing the register transfer level and synthesizing it, but they also do a lot of full custom design, meaning that they place and route some of the transistors but with using their hands over here. And you can see the layout of the chip over here. I'm not going to talk about. Okay, but again, this is not a new idea, actually. The earliest processing in memory paper comes from 1970. Granted, it's a bit different from this because technology was different, but we have actually been working on processing in memory actively for the last 10 years or so. This is one of the papers that actually, I believe, is conceptually similar to what the previous two works, UpMem and Samsung, has introduced. And we looked at specialized processing in memory using graph processing as a specialized workload and showed significant benefits on that. And I believe this is important. We've been looking at simple processing in memory approaches also, so that you can simplify it. We've been looking at, together with Google, we looked at processing in memory on mobile devices. I'm going to actually get back to this work and give you some data points later on. It should be hopefully interesting. We've been also looking at in-DRAM processing. You can see the papers related to this. This is also, I think, going to be more important going into the future. It has a slightly different approach, but hopefully you can see it later on. Again, I don't expect you to know or read any of these papers. This is just to give you an idea that what's happening in research is actually affecting products, and that enables us to teach that as fundamentals going into the future, because you're going to be potentially programming for these in-memory computing engines, even if you end up becoming a programmer, let's say, software engineer, and you don't want to deal with any of the systems, platforms, hardware, devices, circuits issues, you may still be programming for these things, right? Okay, and then research is still happening, actually. In the next month at the ASPOS conference, we're going to talk about bit serial SIMD processing in DRAM and a framework programming, as well as enabling framework for this. And then next week in the HPCA, High Performance Computer Architecture Conference, we're going to talk about synchronization for near data processing architecture. So this is just to give you an idea of, there are a lot of issues to be solved at the architectural level for these new systems. And if you're really, really interested, I would recommend looking into this long paper. Hopefully it's a tutorial paper that was written by me and my postdocs in December to give you an idea. And there's also tutorials related to this that I delivered. And this is the most up-to-date tutorial, let's say, that was invited at the IEDM. IEDM is the International Electron Devices Meeting. This year, or last December, it had the 66th incarnation of it. And it's the cutting-edge conference in devices. Essentially, if you're interested, this covers a lot of the state-of-the-art in processing in memory. It clearly doesn't have the Samsung announcement, because that happened in February, not December, right? Okay, and again, this is just a foreshadowing. We're not going to focus a lot on processing in memory and these really, really new paradigms in this course, because this course is an introductory course. But I have to inform you of what's coming next, because this is going to happen, hopefully. Well, it's happening, as you can see. But if you're really interested in this, you can take the next course after this course, which is the computer architecture course at the master's level. And we have a lot of material related to processing in memory on that, including the UpMem processing in memory engine. Okay, so let me go back. There are other things that are happening. I mentioned this, so I'm not going to spend a lot of time on this. Clearly, people are designing AI and machine learning accelerators. Tesla, a car company, is designing vision processors, machine learning accelerators, so that they can employ it in their systems, customized for the software. They can customize the software and the hardware together, so that they can make the right decisions in their self-driving cars safely, right? Well, hopefully this is improving their systems, right? Instead of trusting some other manufacturer to design the chips that do not necessarily go well with the software that they design, right? That's exactly why they're designing their own chips, so that these chips can do exactly what they want at the software level. They can be energy efficient, and they can actually be safe and secure, and they can be optimized for the vision processing and machine learning applications that are really critical for essentially enabling a self-driving car to see, right? To see and take action, right? Okay, so I'm not going to talk about this. If you're really interested, again, there's a YouTube video that I linked over here. It's actually a beautiful video. It's actually part of the conference, I think, that Tesla organized at some point in 2019. And their chief architect talks about the design of these systems. There are also a lot of software-related talks if you're interested in those. So this is Google's TPU Generation 1. I mentioned that this is actually relatively earlier than the Tesla's chip. And again, a company like Google, a traditionally software company, is investing in these chips because they find this is much better for their system. In fact, they invested a lot more. This is TPU Generation 2. TPU Generation 1 can do inference classification, but it cannot train these large machine learning models. So this one can train these large machine learning models. As a result, it requires a lot more computation capability, as you can see over here. It has high bandwidth memory, which Samsung chip is based on, as opposed to lower bandwidth memory. So it has a lot more chips. As you can see, this is designed for much more powerful computation and applications that can strain the computation much more. You can see also the sinks, right? The heat sinks over here. So it's a beast, let's say. And this is just generation 2. There are generation 3 and generation 4 that we don't necessarily know of. And fundamentally, at the heart of it, this is a systolic array. Systolic arrays were developed in the late 1970s. And they were developed for image processing, actually. Well, image processing was an application for it, let's say. They were developed for convolutions. So today, they're actually very good at executing convolutional neural networks, which is what they were developed for. So in a sense, there's nothing new here. But what's really new is the application and the system design. So fundamental principles of systolic arrays are very, very similar to what they were when they were developed in 1970s, 1980s, as we will discuss in a later lecture. But how we actually take advantage of them, how we actually customize them, how we actually make them work in a real system, and this is an example, is important today. So you can see a little bit more detail over here. This is the matrix multiplication unit. You can do 64,000 matrix multiplication in one clock cycle, as you can see over here in this tensor processing unit. And a lot of the enabling factors are actually in the system software and platform over here. You can see that you need to ensure that the weights of the network get fetched at the right time. The data that you're going to multiply with the weights are fetched at the right time. And everything is orchestrated such that this matrix multiplication happens nicely, right? And again, I'm not going to talk about this in detail. We're going to cover a little bit more when we talk about systolic arrays. We're going to start from the fundamental principles of systolic arrays. That's going to be around lecture 16 or so, I think. So just to give you an example, we're going to build up to how these systolic arrays actually execute. Okay, so there are many, many other AI, ML chips. I'm not going to list them, but essentially all big company and many small companies and startups that you know of that is doing something related to AI and ML are developing their own chips. So I know for sure that, well, actually they're published or they're actually written white papers on their chips, all of these companies over here. Clearly NVIDIA, right? They built GPUs, which enabled the machine learning revolution, but they also have specialized processing units for tensors inside their GPUs as well. And this is one example. You can go to this link if you're interested. I mean, I haven't verified everything, but this looks reasonable to look at, except I think this is a bit older. This is about 2 years old now. And these folks, I think the number of companies that are working on this have increased significantly going into the future. Okay, so clearly AI and machine learning is a very hot application, maybe sometimes overblown in terms of importance. That's also true in my opinion, but clearly it's important, no question about that. Maybe it's overblown in terms of its capabilities going into the future. I think we still need to invest in other paradigms in terms of the capabilities, but these applications are driving innovation across the system stack. Okay, let me jump into reliability and security, a completely different perspective. And this is also becoming very interesting and very tough today also. Let me give you some examples. I mean, if this were a live lecture, I would ask how many people know about the DRAM RowHammer vulnerability. I will still ask. You can feel free to write or raise your hands, but it's not, unfortunately, very interactive. We need to find some solution for this interactivity. I guess nobody said they know about RowHammer, so I'm going to assume that oh, okay, I see some raised hands on some corner of my Zoom. Unfortunately, I don't see everything that you write. So if you are writing something, then I cannot read it because I'm not very good at parallel processing, let's say, because I have to be able to both speak as well as look at the what's written, and I see a lot of things written. So hopefully my TAs are handling that. But I see that a lot of people are raising hands. But this is a new problem, relatively new problem. We actually discovered it around 2012 and 2013 together with Intel. And let me give you the story of it very quickly. We're going to talk a little bit more about it in the next lecture, actually. Basically, this is the phenomenon that you can predictably induce bit flips in commodity DRAM chips. Basically, you can change a 1 to a 0 or a 0 to a 1 predictably without having any permissions. So this should not happen, right? This sucks, actually. Nobody should be able to do this, right? And if you can do this, that means that you can damage somebody else's system. That means that you can take over somebody else's system and become root and take all of their system and private data, etc. So this is not good. And when we actually discovered this, we said that more than 80% of the tested DRAM chips are vulnerable. We demonstrated experimentally and rigorously. And this is really the first example of how a simple hardware circuit level failure mechanism can create a widespread system security vulnerability. And as a result, people are actually developing a lot of attacks. So this is a popular magazine article in Wired magazine. You may be following this. It is actually sometimes nice articles like this. But basically, this Andy says here that forget software. Now hackers are exploiting physics. And I think at a very, very high level, this is a very nice characterization of what RowHammer is about. There's a physical problem at the circuit level that leads to these bit flips. At the software level, you can actually induce these bit flips without anyone being aware of it and take advantage of those bit flips to take over the system, which is not nice. Okay, so let me go into a little bit more detail. I'm not going to spend a lot of time. So if you don't understand it right now, you will understand it hopefully in the next lecture. But basically, this is a fundamental problem. And in memory chips, you have rows of cells. We're going to see this later on also. And if you want to access some data in some row, you need to activate that row, which means that you need to apply high voltage to that row. Now, if you want to access some other data in some other row, you deactivate this row, which means that you need to apply low voltage to that row. Now, if you keep doing this repeatedly, this is essentially a read sequence. Basically, you're reading a row and closing it. Now, if you keep doing it repeatedly, read, close, read, close, read, close, read, close, read, close, read, close, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, it turns out adjacent cells, meaning some row, we call this the victim rows. And we basically said that if you're able to do this hammering enough times before the cells get, can you hear me? I have a question mark somewhere. Can someone indicate that they're hearing me?
Yes, we can hear.
Okay, great, thanks. Because I also received a message saying that my internet connection is not stable. I don't know why, because I'm connected through Ethernet. That should be fast. Okay, good. People are hearing me.
It froze for a moment, but now it works again.
Okay, thank you very much. Yeah, if at any point for some reason it freezes and you cannot hear me, please let me know immediately. Well, assuming it doesn't work within a second or so, so that I don't go forward. Okay, so basically we showed that more than 80% of the chips are vulnerable to this effect that are manufactured by 3 major manufacturers, A, B, C. And there are only 3 major manufacturers in the world, Samsung, Hynix, and Micron. Not necessarily ABC, but those are the 3. So basically, all of the more than 80% of the chips that are in the market are vulnerable to this problem. So let me quickly say why this problem is happening. This problem is happening because cells are very close to each other. Cells are too close to each other. As a result, they're not isolated from each other. So whenever you do this toggling on the word line on this row over here, you're really causing disturbance in physically adjacent rows. And the noise vulnerability of the cells have reduced because they're too small today. And this is a technology scaling problem. So we're going to talk about this more. But let me talk about the higher level implications of this very quickly. Basically, when we wrote the paper 7 years ago, we said that memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. And we basically said that someone can hijack your computer based on what we have shown in this paper. And while we were working on that hijacking, these folks from Google Project Zero essentially showed that. They basically said they learned about the problem from our paper, and they basically said that they could take over a system without, at the user level just by inducing and exploiting these bit flips so that they can circumvent memory protection. So I'm not going to talk about this in detail. This is actually fascinating. This should not happen clearly, right? Whenever you're reading memory, no other location should change. Whenever you're writing to memory, no other location should also change. But here, you're reading memory, you're not even writing, but some other location is changing. And that some other location may belong to the operating system, may belong to some other program, may belong to your own program. So in the end, basically you get something that's not good. It could be bad for reliability. It could be bad for security, as we discussed. So this is now known as the RowHammer problem. And a very famous hacker on the internet basically talked about this problem by saying it's like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. And I like this analogy. It's a beautiful analogy. So if you're stuck in a room ever and the door is locked, start banging on the walls. And assuming that the same sort of disturbance exists between the door and the walls, well, hopefully the door will magically open because the vibrations that are caused by the disturbance that you create on the walls will open the door, right? Okay, that's an analogy clearly. But there are real attacks that are actually built by other folks based on our paper. These folks at TU Graz show that they can gain unrestricted access to systems of website visitors by taking advantage of RowHammer bit flips in JavaScript. These folks from Vrije University in Amsterdam show that they can deterministically take control of an Android phone if you download their app, and this app actually figures out how to attack you with RowHammer. And some similar folks show that you could do these attacks much faster using GPUs. GPUs are something we're going to talk about later on in this course also. These are massively parallel machines. You will see that they're very fast, and they can enable certainly much faster hammering of the rows. Other folks and similar folks actually show that you can do this RowHammer attacks over the network. So take over a remote machine by hammering its memory. Similar, some other folks, actually, these are competing folks, let's say, they basically show that they could do exactly the same thing. So these are repeated many, many times, as you can see. More recently, folks show that you can actually leak private data, even if you may not be able to take over the system for whatever reason. And that's equally bad, I would say. And more recently, well, I guess similarly recently, folks have shown that they could essentially take a neural network and reduce its accuracy to a level that this neural network is essentially useless or harmful. So similar papers were written. So this is at Unix Security last year. Basically, these folks say that you have a neural network. It classifies, let's say, I don't know, whatever thing you input to it with 90% accuracy. If you subject it to RowHammer attack in a customized way, its accuracy goes down to 10%. So this is really bad, right? Imagine that you're using a neural network to detect a pedestrian in your car, and its accuracy is quite good normally. 90% is not enough. You should really be very close to 100%. But with RowHammer attack, it becomes, I don't know, 30% or 10%. That doesn't sound very good, right? So clearly, this sort of reliability and security problem is not good to have in future systems that we rely on. In fact, we rely our lives on, right? So that's why I think this is so critically important. I'm not going to talk about this more, but we're going to go into it as a potential case study in the next lecture. This is the paper that we have written. Actually, we recently wrote a retrospective with Jeremy, my PhD student, on this topic. If you're really interested, you can read it. But actually, this problem did not go away. Recently, we have also shown that this problem is becoming worse. DRAM manufacturers actually put in solutions to the problem, but those solutions are not working. This work actually showed that those solutions can be bypassed because they're not secure enough, essentially. So we're also working on secure enough solutions. But unfortunately, what DRAM was advertised to be secure until 2020, after we wrote our paper. But essentially, that security property doesn't hold. So unfortunately, this is not good. And we also written other papers. If you're interested, we actually have a work that's coming up next week in HPCA that talks about how to securely prevent these RowHammer attacks at low cost with a mechanism called BlockHammer. But again, I'm not going to talk about these in detail in this course. You can read this on your own if you're interested. It's a fascinating topic. It's a great topic to do research on and actually build your creativity on, let me put it that way. But that's it. So, okay, if you're really interested in learning, if you cannot wait, and if you really want to learn more about it, this is a recent lecture that I delivered in the High Peak conference that talks about the story of RowHammer. And this is essentially covering the state of the art. This was last month. Okay, and we have more lectures. So again, this course will not go into a lot of advanced concepts. We're going to use RowHammer to motivate and show that there are important problems at the lower level. There's plenty of room at the bottom, for example. But if you're really interested, we cover this a lot in the computer architecture advanced course, and also in the seminar course, which some of you are going to probably take, because usually students who take digital design and computer architecture end up taking the seminar. But of course, seminar is limited to only 22 students. Okay, so that was RowHammer. So, and that's just one example. But there are other things that have also happened recently. Probably more people know about Meltdown and Spectre. How many people know about these examples? I see some hands that are raised. Yeah, sometimes we will do polls. I figured out how to do polls in Zoom, but maybe we are not going to do that right now. So these Meltdown and Spectre are also hardware security vulnerabilities at a different abstraction level. Essentially, these happen because of the algorithms that are employed in the microarchitecture of processing general purpose processing units, and almost all general purpose processing units that are high performance today. So RowHammer was a physical effect, right? It was circuit level. This is a microarchitecture level problem that leads to security issues. Essentially, I'm going to give you the high level perspective. Maybe we'll go into a little bit more detail depending on how next lecture and next week pans out. But basically, similar to RowHammer, someone can steal secret data from the system or take over the system potentially if you're really, really good. I think these attacks are actually harder to do compared to RowHammer attacks, because RowHammer leads to a bit flip directly. If you can somehow exploit it, that's easy to do. Whereas Spectre and Meltdown, you need to actually really know what is really going on in the system to really leak the data that you want. Again, I'm not going to go into detail. I'm going to refer you to a paper. But this happens even if your program and data are perfectly correct. Your hardware behaves according to the specification. So that was not true in RowHammer, right? In RowHammer, your hardware does not behave according to the specification. Hardware should really not get a bit flip if you're not changing that particular bit. But Meltdown and Spectre happens even when your hardware behaves according to the specification, and there are no software vulnerabilities and bugs. So why is this happening? Basically, we're going to actually cover the concepts in this class. We're going to talk about speculative execution, for example, when we talk about pipelining, branch prediction. Existing processors speculatively execute programs. Whenever they get to a branch, they don't know which path to go, so they predict which path to go. So they speculatively execute a program, user program, to maximize performance. But the speculative execution leaves traces of secret data in the processor's cache, because during the speculative execution, some locations get accessed, even though the program may not be allowed to access them. So you update your internal storage. We're going to cover caches also in this course. So even if you don't understand anything over here, just understand that we're going to cover a lot of the basics that will be required for someone to launch these Meltdown and Spectre attacks. So basically, it brings data that's not supposed to be brought or accessed if there was no speculative execution. And speculative execution is there for performance reasons. Okay, now a malicious program, what it can do is it can inspect the contents of the cache to infer what is the value of the secret data that it's not supposed to access. So some other program brings us data, or maybe the malicious program brings the data, depends on how you construct the attack. And then you basically check the contents of the cache to figure out what is the data values. Not good. And actually, you can go even further. If you really know what you're doing, if you know the microarchitecture really well, a malicious program can be constructed to force another program to speculatively execute code that specifically leaves traces of secret data. So you can actually target these attacks very, very carefully. Of course, it's not easy to do these attacks, right? You really need to have an extremely good understanding of the underlying hardware and microarchitecture. Again, I'm not going to go into the details of this, but this is something that's exciting that's happening today. I would recommend you take a look at Google Project Zero, Jan Horn's blog post over here, and their papers also on these topics that I did not put over here, but you can find them easily on the web since they're so popular today. But basically, today, security and privacy are becoming very, very important concerns. Reliability also on top of this. Designing robust systems are much, much more important than ever, because we're going to trust our lives, cars, self-driving cars, or many, many different aspects of our lives, decision-making in terms of related to our health, etc., on these computers, these intelligent systems. So if they're actually vulnerable to this sort of problems, it's not going to be a good future going into the future. So one of the important things, hopefully, that you will get out with the fundamentals in this course is, in the back of your minds, actually, at least, how do we actually fix these problems going into the future at different levels of the stack, given that you know exactly how the computers are operating today at the end of this course, of course. Okay. Okay, now let's move on to something else that's happening in computer architecture as well as system, and that's more demanding workloads. I mean, we kind of talked about this, right? We talked about AI, ML, but applications are increasingly demanding. And this is really up to the imagination of people. You dream and applications will come. So it's actually interesting. There are actually a lot of anecdotal stories that I can tell you. When MIPS R2000 was designed in early 1980s, we're going to cover the ISA MIPS. And the first incarnation of it was in early 1980s. You're going to do your labs in MIPS, actually, some of your labs in MIPS ISA, so you will learn it. But MIPS R2000 was a very simple processor. And some folks basically said, this is the best processor we will ever have. Why do we want a more powerful processor than this? Clearly, they have been proven wrong many, many times over, right? So basically, the thinking was that, okay, we have the best applications that we can have. Let's give up. No, that's not going to happen, basically. People will always be dreamers, and they will dream, and they will create new applications. And that's how innovation will proceed going into the future. And these applications will be extremely demanding going into the future, exactly how machine learning training was. And essentially, there will be a need for increasingly powerful and increasingly efficient and increasingly secure computer architectures, because computing platforms will become increasingly strained as applications push boundaries. So if somebody says that we're done with applications, never trust them. Let me put it that way. Dream, and you will bring something. Okay, some applications that I think are not very well enabled today are these devices, for example. This is Nanopore Sequencing. This is a sequencing device that you can yourself buy for $1,000, let's say. You can actually start sequencing genomes around you if you're interested, including your own. But basically, these devices are capable of doing high throughput, low latency, or at least low latency by today's standards, processing of genomes, and they generate huge amounts of data. And today, we don't have the capability to actually process this data so that we can do really, really meaningful studies at low latency with them. We can process the data from them waiting for 2 weeks or, I don't know, hours. But if you want to give this device to a doctor, for example, and doctor would like to make a critical decision in the life of a patient in terms of what drug to administer to that patient, we cannot do that today. You cannot do the decision. You cannot make the decision within a minute. You have to wait, I don't know, depending on the complexity of the analysis and depending on the question. Sometimes you may not be able to get the answer because you don't have enough data. But if you are able to get the answer, it may take days, weeks, or if you're lucky, hours, basically. Minutes are not imaginable. But I believe minutes have importance, basically, because there are cases where you need to critically decide. And also, if you reduce the latency of these things, you can enable the speed of innovation, right? Even if you're not constrained by a decision that you need to make a minute, if you're actually able to generate new insight quickly within minutes, then you can actually increase the level of innovation and speed of innovation in science also. Okay, so these are genome sequencers, and they're mainly bottlenecked by data. So there's a huge performance energy bottleneck, but I believe these applications are going to become increasingly important. So another reason why we care, this is actually a slide that I first used in the digital design and computer architecture course last year. I think I used it in the first week of February. You can see that the date over here. But basically, that was one of our the earlier lectures, in-person lectures at the time. And basically, I mentioned that there's this COVID-19 outbreak and sequencing is becoming very important. And people actually, you can see in this news item, Nanopore sequencer are shipped to China at the time. It was only in China at the time, or it was only said to be in China at the time. People were actually using these Nanopore sequencers to actually understand what's going on with the outbreak and the evolution of the disease at that time. So clearly, these sequencers have been used many times over the last year. So they're proven their worth. But unfortunately, they're still not capable enough in the sense that we cannot really analyze the data efficiently and quickly enough inside the device, for example. So there's a lot more to do in these platforms. And you can imagine doing population scale profiling, microbiome profiling, so that you can understand what's going on. You can predict outbreaks potentially if you're actually able to do that. So this is one example paper. I'm not going to expect you to read the paper, but these folks collected samples, for example, from the New York City subway, and they basically tried to understand the bacterial diversity in the New York City in different areas. So these are enabled by these genome sequence analysis devices or RNA analysis devices, etc. Essentially, these devices that do sequencing. But clearly, it took them a long time to be able to do that. So these are some applications of these devices. Of course, we're very much bottlenecked by computation and platforms today. And this is another example. This looks like old news, but this is actually a paper that was published in Nature in 2016 related to the Ebola outbreak. You can see that the title of the paper is Real-Time Portable Genome Sequencing for Ebola Surveillance. Now, this sounds familiar, right? Today, we're dealing with COVID-19, not Ebola. But you can see what portable means. This is portability. You can put it on a cart. And you can see what real-time is. Well, I guess you need to read the paper, but it's not really real-time. What I consider real-time would be a minute, let's say, or a second. In this case, it's more like a day or maybe longer. So they kind of set up an office to actually do the Ebola outbreak surveillance in Guinea over here. And I think it's fascinating how the technology is going to evolve into the future. At that time, nanopore sequences were not as common at the time. But I think we need much more powerful sequencers and sequencing platforms. And these are some other sequencers that I'm not going to talk about here, and all produce data with different properties. So doing sequencing inside the device is becoming interesting. And you can see the sequencer over here that you can plug into your cell phone, right? So I think the future is very bright in terms of technology. And this is actually an example of there's plenty of room at the bottom, right? You can see that these sequencers are operating at the very, very low nano scales, very similar to what was envisioned by Payneman in this 1959 talk. And clearly that's happening. And I think more is going to happen. But in order to enable what's coming out of those sequencers, we really need to do a lot on the top at the algorithms and higher level sides, as well as the system designs. So I think these sequencers, the cost of sequencing has been reducing dramatically. Soon we will see Moore's law. Moore's law basically specifies how fast the cost of a transistor is reducing. You can see the curve is like this. Oh, it's exponential actually, but it's a log scale over here. That's why it looks linear over here. But basically, the cost of sequencing is actually reducing a lot faster today. So it's actually a much bigger exponential than Moore's law. As a result, we can sequence many more genomes. The question is, can we actually do something really, really intelligent about them quickly, such that we can enable much better scientific discovery and much better health and medical applications? I think we're very limited by computation today, actually. We've been working on this area for some time now, since actually almost 12 years now, right now, more than 12 years, 14 years, I should say. But there are some papers that we have written recently. FPGAs, which we're going to use in the labs of this course, are actually going to be important computational devices to improve the efficiency and performance of genome sequence analysis. In-memory computation is going to be also very important in genome sequence analysis, as you can see in these works. Algorithm architecture co-design is going to be very, very important. This is an example of algorithm architecture co-design. This is a more recent example of algorithm architecture co-design that can work on CPUs, GPUs, and FPGAs. And we're interested in doing it on in-memory computation also going forward. This is another algorithm architecture co-design for approximate string matching, which can be used for many tasks in genomics, bioinformatics, and also text, etc. So basically, the future is very bright, I think. And I think it's enabled by both bottom as well as the top. So remember the axiom we had. I think this is another example. But people are dreaming of these applications, essentially. Let me quickly spend some more time. These slides I did not use at the time because these were not available last year when I was giving the earlier lectures that I showed you a slide from. But basically, this is what's claimed by the Nanopore tech company. They basically say whole genome sequencing of COVID-19 takes 7 hours. Okay, this is debatable, I think, depending on what analysis you do, of course. If your analysis is huge, like you're comparing millions of different genomes, then I think you're lucky to do it 1 hour. But basically, they say it takes 7 hours from RNA to answer. But even 7 hours is too slow, I would argue. In fact, they have this nice picture over here where they talk about metagenomic nanopore sequencing. Basically, you basically characterize co-infecting bacteria and viruses, identify correlation and risk factors of different patients, research potential future treatment implications. You can also investigate what might cause different responses based on different genomes. And you can also track potential mutations, etc. To be able to do all of that, it's not 7 hours. It'll take you much, much longer than that, 7 days, even more. Right? So it's actually, we're very much bottlenecked today by the computing platforms, even though the fundamental sequencing technology is able to produce data very quickly, as you can see over here. these folks claim that you can sequence only within 1 hour, right? So the fundamental sequencing technology is not bad, but the analysis is actually much longer today, depending on the analysis that you want to do. Okay, so if you're really interested in this area, we're not going to talk a lot more about this in this course, but I think all of the fundamentals that you will learn in this course would be useful for enabling applications like this. But we recently written this short survey paper that talks about issues in accelerating genome analysis in a broad perspective. And I've also recently, last month, delivered a lecture that covers even more issues in genome analysis. If you're interested, you can actually take a look at those. But none of this is required, actually. This is just for your benefit if you're interested in these areas, because I think there's huge potential for people like you who are just newcomers into the field to understand and improve after learning the fundamentals, the state of the art, because we really need those improvements going into the future. Okay, and of course, as I mentioned, we cover this sort of stuff really in the more advanced course, computer architecture, and the seminar in computer architecture, and you can take a look at those later. Okay, so genome sequence analysis is clearly a very, very constraining application, but there are other applications today we're very constrained like databases. Clearly, all of you are using these applications knowingly or unknowingly. Databases are not scaling very well. Graph and tree processing is not scaling very well. Clearly, their data center workloads. All of these applications are shown to be bottlenecked in terms of performance and energy by data and existing computational platforms, essentially. Now, if you look at the mobile end, the story is very similar, actually. These are some old applications, but you can imagine innovating new applications, right? Chrome, TensorFlow, machine learning frameworks, video playback and capture, which is what we're doing right now, actually. We're all doing video playback and capture in our systems, and we're all experiencing the bottlenecks internally. I guess we're lucky that we have constant power. If you didn't have constant power, unfortunately, what we're doing right now wouldn't have been feasible, for example, or if we were really power constrained, that wouldn't have been really feasible. If some of you may be power constrained, you may be watching this on a device that's very power constrained, and as a result, you may not be getting great quality. I don't know. But basically, all of these applications are in the end are bottlenecked by data, and performance and energy is really bottlenecked by the capability of today's computation platforms. If you want to really take them to the next level, for example, if you want to have a very intelligent learning engine on your cell phone and enable training of your of big models in your cell phone so that you can actually learn something important about your health, etc., such that this thing can actually really integrate with you as opposed to you querying this thing once in a while, then actually we're far away from that. Okay, so let me give you some number related to the study that we did with Google over the course of 1.5 years. This was published in 2018. And we studied these 4 workloads that I showed you over here together with Google. And we basically showed that more than 60% of the total system energy is spent on data movement on these workloads. Real workloads, real input sets, executed on real devices, mobile devices. Now, this, I believe, is unacceptable. You are consuming 60% just to move the data to the computation units across the memory hierarchy. So this will become more clear when we cover how a computation unit gets the data, but imagine that 60% is a big fraction, right? Okay, let's see. So I'll give you one other data point over here in today's systems. Basically, this is a picture that analyzed the costs in terms of energy of different operations. So you're going to see some of these operations. Well, maybe not the double precision floating point operation, but imagine that this is a floating point addition. It's an addition on a big number, 64 bits. It takes about 20 picojoules today. Now, a memory read or write to bring the data that's needed by that operation, just one element, to bring one element is 16 nanojoules. Now, if you do the calculation, that's an 800x difference. So a memory access today is actually somewhere between 2 to 3 orders of magnitude. The energy, it consumes the energy of a complex addition. So that's a lot, basically. So that is unfortunate. Now your data access is really consuming a lot of your energy. And also it takes a lot of latency, which is not reflected in this picture. Okay, so it's good to keep this in mind because we're going to later talk about computation, memory access, how you actually fundamentally enable it. And we're going to bring a lot of data into the processor so that we can process it. But maybe that's not a good design choice, right? In the future, maybe there will be processing in memory engines so that you don't actually bring the data, you actually move the computation to the data because doing the computation is much less costly in terms of energy compared to moving the data. Now, very briefly, I must also mention that this picture was very different 70 or 80 years ago. So if you were taking this class in its current form 70 or 80 years ago, your instructor would have been telling you that a complex addition operation is about 2 orders of magnitude more costly than a memory access. So that's 2 orders of magnitude worse energy for computation to memory access. Today, it's exactly the opposite. 2 to 3 orders of magnitude worse energy for memory access compared to computation. So why did this happen over the course of 70, 80 years? And the answer is technology scaling. Essentially, we will talk about Gordon Moore and Moore's law. Moore's law and technology scaling, the ability to reduce the size of a logic gate and a transistor in CMOS technology enabled us to do essentially that, reduce the size of that logic circuit, which reduces its latency, which also reduces its power consumption. So we basically did that very, very successfully over the course of 70, 80 years. As a result, these arithmetic units became extremely efficient, but unfortunately, we weren't able to do that as well with memory for reasons we will discuss later, because memory is not completely logic. So it doesn't scale as well as logic. Okay, keep that in mind. That's another historical perspective that I wanted to give you. So if you were taking this class 70, 80 years ago, it might be actually very worthwhile to work on computation and its efficiency. Not today. Today, actually, you're in a very different trade-off space. It's really all about memory access in many applications. Of course, some applications are computation bottlenecks. Sure, there you need to work on computation. But today, it's very much about memory access, and you're bottlenecked by memory access. So it makes a lot of sense to figure out how to deal with that. As a result, you can see exactly the example architectures that I showed you, the Cerebras wafer scale engine. The goal is to bring computation and memory together as much as possible so that you don't go off chip, such that your AI accelerator becomes efficient. In Samsung's FIM-DRAM, function memory DRAM, designed for AI applications, essentially the same goal in a different way. They basically design a memory chip that can do floating point, multiply, and accumulate operations, as opposed to doing those operations in the CPU here. Similar to UPMEM, UpMem architecture, right? Essentially the same idea in the end in different realizations. Okay, so keep that in mind. So today, many interesting things are happening in computer architecture because of all these reasons. I've given you a tour of it. Now, let me actually conclude relatively quickly. Basically, many novel concepts are investigated today. I gave you some examples. There are new computing paradigms. We want to rethink the full stack, processing in memory, processing near data, neuromorphic computing, fundamentally secure and dependable computers, and there are more that I don't include over here. Quantum computing is one example that's a bit farther out, I think. It's not as general purpose, frankly, as some of these other things like processing in memory. There are new accelerators, algorithm hardware co-designs for important applications like graphs, graph analytics, artificial intelligence and machine learning, obviously, and genome analysis going forward. And there are new memories and storage systems like we discussed, non-volatile main memory, processing in memory, intelligence inside the memory, using machine learning concepts to improve system decisions in memories as well as architectures. So this list can be expanded. I gave you some sampling over here. But basically, applications are not a problem. We're dreaming and applications are coming. There'll be more. And trade-offs are becoming increasingly diverging and complex. I gave you the example. I'm not going to elaborate on that again. So we need to actually think differently going into the future. So hopefully in this course, we are able to give you the ammunition to think critically and differently so that you're not optimizing the wrong thing. So if your application is bottlenecked by memory, go and optimize memory. If your application is bottlenecked by computation, go and optimize computation, right? If your application is bottlenecked by neither, but you really have security problems, go and fix your security problems first. Usually your application is bottlenecked by one of them, by the way, computation or memory. Okay, and increasingly complex systems we have today. Past systems look kind of like this is a general purpose system, but you have processors, main memory, storage. Modern systems are increasingly heterogeneous. You have heterogeneous cores inside a processor. You have dynamic and static heterogeneity. You can dynamically change the frequency and voltage. You can dynamically enable and disable cores. You can have GPUs over here. You can have multiple different types of GPUs also. You can have FPGAs, reconfigurable logic. You can have multiple different components connected to memories that are also heterogeneous. Some memories are fast, some memories are slow. And then you have some persistent memory and storage, which may also include the non-volatile memory. So modern systems are increasingly complex and heterogeneous, basically. So they're not easy to manage, but they enable much more opportunity than before. So as a result, computing landscape today is very different from 10 to 20 years ago, even 5 years ago, actually. A lot of the innovations that I showed you happened in 2019, 2021 timeframe. And again, this slide I already used, applications and technology both demand novel architectures. And as a result of everything that I described, every component and its interfaces, as well as entire system designs, are being re-examined today. So I'm going to conclude with this set of motivating slides. I believe as newcomers to the field, you can revolutionize the way computers are built, or how we think about computing actually in general, if you really understand both the way hardware and the software are designed, should be designed, and how you should really change each accordingly. You can really invent new paradigms for computation, communication, and storage, and this can enable really big changes in the field. And again, I recommend a lot of stuff in my lectures, as you can see. This is another book that I would recommend. It was written by Thomas Kuhn. It's a philosophy of science book. It basically covers a lot of scientific revolutions in physics, chemistry, astronomy, etc. It basically analyzes the structure of them. It basically says that there are some cases where science is not satisfactory because there's no clear consensus in the field. And scientists try desperately to find something that explains the phenomena. And hopefully, they would like to be in normal science. There's a dominant theory that's used to explain things, business as usual. For example, the sun, the Earth revolves around the sun, right? This is something that we take for granted. This was not something that we should have taken for granted if we were living 800 years ago or 1,000 years ago, right? At some point, this was questioned, and there were exceptions. There was a lot of evidence that built up such that people started thinking, oh, it's actually the Earth is rather, the sun is not revolving around the Earth, actually. It's the other way around. And over time, there's a lot of resistance, clearly. There's always resistance against good science. And as a result, people basically say there's no dominant theory. But at some point, revolutionary science emerges, and people start re-examining the underlying assumptions that have been there in place for a long time. And they design new things that can lead to new paradigms. Today, for example, I believe there's no clear consensus in the field of computer architecture in terms of how to best execute workloads and how to best design the systems, because it becomes very application specific. Now, 20 years ago or 30 years ago, the consensus was clear. We have a single core system, as we will see in this lecture, early part of these lectures. You optimize that single core system that executes a single thread as much as possible. You maximize its performance, and you're done. It's good at general purpose applications. But today, the landscape is extremely different. That single core system did not work well for energy, did not work well for new applications. It did not scale. So technology scaling issues made sure that there was a lot of complexity in the design. So basically that consensus disappeared. Now we are in the revolutionary science where we're really re-examining new paradigms for computer architecture. And I think I would also say computing in general, because you're going to be taking some theory of computing courses. So if you take theory of computing courses, you mainly talk about the number of operations to discuss the complexity of algorithms, right? But maybe that's not the right way, right? It's good to question critically if what you're really bottlenecked is the data and not the operations that you're doing, like I showed you earlier. Maybe you should really rethink the fundamentals of the theory of computation also. The big O notation, some of you may be exposed to it, for example. The big O notation counts the number of operations to determine the complexity of an algorithm. Well, maybe that's not the best way going forward. And this is Thomas Kuhn, and this is his book, if you're interested. So let me conclude with this slide. Today, I believe it's an exciting time to be understanding and designing computing architectures. There are many challenging and exciting problems in platform design that no one has tackled or even thought about before, actually. And this can have huge impact on the world's future. As you can imagine, right? We're all relying on AI, machine learning, self-driving, whatever you can imagine. And today we have a lot of new applications. We're driven by a huge hunger for data, big data, hopefully for good reasons. But clearly, technology is agnostic to morality or ethics. There are people who will have bad reasons to actually mine the data, but there are good reasons for doing so also. So bad reasons should really not deter us from developing the technology. We just need to be careful about how we potentially are protected against those bad reasons, right? That's why privacy and security are very important. So there's a huge hunger. There are new applications, as we discussed. There's a need for even greater realism. And we can today easily collect more data than we can analyze and understand. And that's training our platforms a lot. So that's one thing. This is the application perspective, workload perspective, data perspective, right? At the lower level, this is a top down. At the lower level, bottom up, we're experiencing significant difficulties in keeping up with the demands of the workloads at the technology layer. There are energy problems, reliability problems, complexity problems, security problems, scalability problems. And basically, that's why we need to consider both the top workloads, algorithms, etc., and system software, etc., and the bottom, which is really the devices, circuits, logic, and architecture is right in the middle of all of that. It really enables you to actually bridge the gap between algorithms and the devices, such that you can exploit the capabilities of both in the best ways. That's why I find architecture to be really exciting, both where it is today, as well as it being in the middle of the stack. And it's really enabling the algorithms on top, enabling the technologies at the bottom, enabling both of them to meet in between, such that you can solve real problems going into the future. Okay, so this is a really great time to stop. I did not take a break this time, so you can use the remaining time for break. In the future, we'll try to take some break. We'll figure out a good way. But in the next lecture, we're going to start with some puzzles. Hopefully, they will be interesting. We will still try to motivate. And after that, we're going to talk about the labs and go into transistor as a building block.